Good afternoon, everyone, and welcome to the Parsons Technical Webinar Series. I'm your host, Jessica Bennett. Today, we have with us Ron Crosscheck and Sam Kermis presenting on drones for orphan wells, applying modern solutions to a century-old problem. A few housekeeping items up front. We'll be keeping all phone lines muted during the presentation to keep any background noise down. If you have any questions during the webinar, you can either enter them into the chat at any time, or you can raise your hand at the end during the Q&A session and ask them live. This webinar has been approved for one Professional Development Hour credit, or PDH. If you are an engineer, or scientist, or geologist, and you'd like to get that PDH certificate, there will be a link to an attendance form that we'll post in the chat a couple times during the presentation. There are going to be 4 multiple choice questions on that form that you'll need to answer based on the presentation content. So please take a look at those, and we'll post those questions in the chat in case you have any issues getting to the form during the presentation. Please let us know if you'd like that form and cannot access the link once it's posted. And finally, this webinar is being recorded, and it will be posted on our YouTube channel in the next few days. So a brief agenda. First, I'll introduce our guest speakers today, followed by a core value moment. Then we'll get into the technical presentation, where our speakers will touch on a few topics of traditional well locating techniques, how to leverage new technologies, and then the results of a pilot study. And then finally, we will wrap up at the end with questions and answers. So a little bit about our 2 speakers today. Ron Crosscheck has over 17 years of experience in oil and gas with Parsons, including plugging and abandonment of early era wells, risk analysis, bioremediation, hydrogeological investigations, remediation systems, permitting, and contractor and safety management. He holds a Bachelor of Science in Mechanical Engineering from Saginaw Valley State University. Sam Kermis has over 5 years experience with Parsons to date on various geophysical projects. He primarily supports Military Munitions Response Program, or MMRP, sites with detection and classification and removal of unexploded ordnance. He also has experience with drone magnetometer, GPR, and electromagnetic surveying, locating orphan wells, subsurface utilities, and anomalies in concrete. Sam holds a Bachelor of Science in Geology from the University of Wisconsin-River Falls. And with that, I will hand it off to Ron for the core value moment.
Thank you, Jessica. At Parsons, we hold 6 core values key, being safety, quality, integrity, diversity, innovation, and sustainability. With our topic today, we're going to focus on sustainability and safety, because with there being over 900,000 orphan wells in the United States that need to be reinvestigated or abandoned, we need a sustainable approach in order to address these. Where that comes in is we're finding out with drones and unmanned aerial equipment that we can remote sense and do a lot of work that would take large factors of magnitude longer if we were doing it on the ground with personnel versus in the air. It's also far less intrusive and very minimal impact on any of the ground. And it is becoming very affordable and even a cost savings option, especially when you enter in a large group of sites. It really drives the cost down to a fraction of what it would to put somebody out there tromping through the woods to find these things. And it also, getting all your information up front, also helps you better plan for remediation and really minimize your remediation footprint. The other fact of it comes in with safety of your ground personnel. A lot of these orphan wells have been lost to time and are in areas of very thick brush, overgrown roads, a lot of forestry or mountainous areas where there could be poisonous plants and animals that people can come in contact with. And some of the scientific instruments have not been the most ergonomic and are sometimes a bit unwieldy, especially when in these challenging environments. So first we'll enter into how we traditionally find previously abandoned and orphan wells, such as in this picture. This one's pretty obvious because the old standard derrick footings are still there, marking where the wellbore location can be. And so when we're locating traditional wells, a lot of times, if a state's good on the records or if they're from a certain area, there may be records or permits available with surveyed locations or state databases with approximate wellbore locations that you can reference to find these. If there are a lot of the old era abandonments, a lot of times they didn't do a great job necessarily cleaning up the site, even up to the standards of that time. And there are a lot of clues such as concrete debris or even the well heads and well casing still sitting above ground, like in these photos, that make it relatively easy to locate. Now you can also find the wells, with any signs of contamination and ground impact, lack of vegetation. And then sometimes if all else fails and you don't know where it's at, you have to dig with heavy equipment in order to find the well bores. If there is well casing left at surface, you can use your traditional metal detector Schonstedt, less than 15 foot in depth the casing to be able to pinpoint the casing on where it may be. Now, locating some of these wells, and especially the earlier abandoned ones, have a lot of challenges. Before and during World War II, a lot of the casing was pulled from the well bores for either reuse or for scrap, especially during World War II, leaving really no detectable area from surface to which you can locate the well with. As you can see in the picture of that mudded well bore, you basically just have to dig to find where that original borehole is, if they even mudded it up that well and it didn't collapse. In many cases, especially in some of the Appalachian states and where the real early era booms were, there were no records or permits of wells, and they are truly unknown. Then you can enter in difficult and wooded terrain, thick vegetation. Once again, the hazards to just being in the woods from poisonous and venomous species. And then if you say in general where your well is supposed to be, but it could be anywhere within a half acre to an acre clearing. It takes a lot of time, effort, and money to use yellow iron to excavate and actually find that well bore. There also could have been subsequent land use changes, such as large problems out on the West Coast, and especially California. That was a big oil state where a lot of these now are in the suburbs under real estate developments, things like that. And then also, if these are in very agricultural areas, the ground is regularly flattened, ripped, tilled, and a lot of the surface evidence of where the well bores are simply disappear. So enter in the science of magnetic well locating. At Parsons, we've been doing this for 12 or 13 years now. And basically, it comes back to remembering your middle school science classes where you're playing with that bar magnet and iron filings and looking at the resulting magnetic field created by the iron filings. That is very similar to what happens to a oil well casing that has over time been magnetized by Earth's magnetic field. We can use cesium vapor magnetometers to perform surveys on the grounds in order to map these magnetic fields, and we can do these surveys in two ways: of walking on the sensor over gridded areas, or using the GPS that's in the picture of the gentleman with the magnetometer system. But as you can see, that is also a 30 to 40 pound plus instrument. And as you can imagine, with that GPS antenna sticking over your head and carrying a 7-foot weighted pole, it may be difficult to climb up and down hills and really hazardous to get good data going in and out of brushy wooded terrains. This method is fairly reliable, however, for where the casing may be within 100 feet of surface. So entering in a little bit into the science, basically that wellbore is creating a vertical magnetic dipole. When you have shallow casing that's close to the surface, you get a very strong and steep slope anomaly. That's generally a smaller diameter magnetic field, which is represented in the red arc on the image to the left. And then as the casing gets deeper from surface to the top of it, it becomes a lower intensity and much larger diameter anomaly that we are trying to map to find the center of. And then the depth of the casing is roughly proportional to the anomaly of the radius. So if you know about where, from any historical plugging abandonment records, where they ripped and recovered the casing from, you can generally get an idea of how big that anomaly is going to be and how big of a survey grid you need to run over it. And then and a lot of these sites are very well littered and marked with a lot of buried debris, which can be some challenges to magnetic location. But generally, when we see that, we can filter that out because it's a lot of times a different polarity of magnetic field than what the well casing is. So these are two examples of ground magnetic surveys we have performed to locate well bores. The one on the left being a well where they ripped the casing off 70 feet below the ground during abandonment. As you can see in the center of that heat map is basically like a bullseye, would be the wellbore location. And I believe on that one, when we actually went and excavated it, we were within 2 or 3 feet of where the GPS point we made on our Trimble GPS to go out and take it out in the field to where they actually dug up that wellbore. And the same thing with the photo on the heat map on the right, showing a much cleaner picture of a well casing that's only ripped off 30 feet below the ground surface. However, as you can see, we ran a very large survey grid thinking where the well was at. However, even then we didn't necessarily get that well bore centered in it, but we still had enough to where we could locate it. That is also one of the issues is, you may do your preliminary survey and then have to redo and move your survey grid in order to then cover where where the well actually finds up being to pinpoint it exactly. But in the case of this ground magnetometer survey where the well was casing was ripped off at 212 feet, that generally looks like a Jackson Pollock painting. This ground survey was inconclusive. This survey was performed on a side hill location adjacent to a cedar swamp. There was way too much groundwater to excavate this site very, very thoroughly with a yellow iron and try and find the well bore without the excavation wanting to collapse in on you and losing the bore. And the area that we could have performed this gridded survey and walked was far smaller than the anomaly that we needed to map. Therefore, we were only really seeing the very more flat top part of that dome magnetic field. And so we couldn't identify where necessarily the center of it was, which it's time to leverage technology and get a larger picture of the site. So a little bit of background on Parsons drone and geophysics programs. We have been operating UAVs for over 15 years. We have 25 plus licensed pilots between the US, Canada, that are all FAA or Transport Canada certified. We regularly do inspections, traffic monitoring, constructions, and surveying with our drones, along with optical imagery, LiDAR, thermal magnetometers, radio spectrum analyzers. Now for geophysics, we have 30 plus years of remote sensing, anomaly detection, and classification. Our primary geophysics has been for investigation and remediation of sites contaminated with UXO or unexploded ordnance for the military. And our first Department of Defense contractor to achieve accreditation under the Advanced Geophysical Classification Accreditation Program. We also use drone-mounted sensors to scan marshes, cliff faces, and other difficult areas with magnetometry, photogrammetry, thermal, and LiDAR techniques to locate the unexploded ordnances. So for a project for a private oil and gas client we had a new list of sites that were added to our project that we needed to go out and do our field reconnaissance and actually locate where these well bores are in order to then go in and do phase 2 investigations to determine if the wells are leaking and if there's any soils remediation that needs to happen. These wells were located in a area of state forestry land that was very dense, very mature, and had very limited access. Essentially, they had been abandoned and forgot about for over 50 years and totally overgrown. So we wanted to see if we could use remote sensing and various other technologies to locate and map these abandoned wells and any remaining associated infrastructure. Out of our suite of sensors we had available, we picked aerial magnetometry, LiDAR, and thermal imaging to try out in a pilot study to assess the ability to locate these wells without any surface casing even present. Like I said, we had dense forested areas that had real limited accessibility. So this is a great real world field study. We didn't go out and just cherry pick some nice wells and easy clearings. This was definitely a real world pilot study of the type of conditions you can face trying to find previously abandoned and orphan wells. We also wanted to do our ground elevation surveying. That way, for any necessary permitting for access and remediation, we had all that data collected up front in one mobilization and didn't have to come back with another surveying contractor and cut lines of sites through the brush in order to, use robotic total stations, because you weren't going to get enough GPS signal under the canopy to get an accurate survey. And we also wanted to locate any former infrastructure such as berms and trenches or former access roads. So for this study, we utilized 3 drones. We had basically a small compact drone that we used for thermal mapping and reconnaissance. We had a medium drone that we used more as a backup, and if any we needed to pack into any small clearings to do smaller flight areas. That drone could carry about a 20-pound payload. And then we had our large heavy lift hexacopter with extended range that we used for the bulk of the magnetometer and LiDAR flights because it had a 50-pound payload capacity. For sensors, we chose an aerial magnetometer that was made to be UAV mounted, very lightweight. It could collect 1,000 samples per second, had integrated GPS with a pretty standard 3-meter accuracy for a non-post-process GPS signal. And it had a 20,000 to 100,000 nanotesla detection range. Our LiDAR sensor could collect 720,000 points per second for the point cloud and had about a 0.2 foot accuracy if flown at 150 foot elevation, which for our survey needs and for permitting was plenty accurate enough. And then we also flew an infrared, long-wave infrared camera with a 32-degree field of vision. So we selected 3 legacy oil field areas which to perform this pilot study. Area number 1 was 130 acres. Area number 2 contained 80 acres, and area number 3 contained 20 acres, of which we would completely map. We did add an additional 10-acre area that had 2 wells. That was in basically an open clearing, just so we could test integration of the different sensors and test out our methods. So total, we expected to find 13 former oil wells, 3 former tank batteries, and 1 geologic test hole location between all of these areas. And from the previous abandonment records, the casing depths ranged anywhere from just below surface to up to 180 foot below ground surface. So very real, once again, real world on wells we would struggle to find with ground methods. And these are also sites that were, fairly early era boom between 1931 and 1957. So areas 1 and 2 were once again in that state forest land, had high density mature conifer trees, The area number one had 120-foot canopy height. Area number two, which had 3 wells and 1 tank battery, and was the 80-acre parcel, was more state forest, but it had been logged off probably about 10 to 15 years ago and had moderate density of conifer and deciduous trees with 40 to 50-foot canopy height. Area number three had 2 wells and tank battery. It was a 20-acre, just a small lease that had 2 wells. These were drilled in 1938 and plugged around 1948. This was going to be the most challenging one because both of these wells were fairly deep below ground, where they ripped the casing off at 163 to 183 foot top of casing. And we also had pretty dense deciduous forest with 80-foot canopy. As I mentioned earlier, our 10-acre test plot that we flew our sensor integrations on had 2 oil wells with tops of casing between 109 and 132 feet. And it was very open, so we could really test to see how things were going to fly. So as you can see in the photo here, this is how we generally set up our sites. We did have a site safety officer, our ground crew members. We did have a designated launch and landing zone. And then we had our aerial man lift that contained our pilot and visual observer. As you can see, this is a very small envelope clearing, which is basically all we needed to be able to launch and land our drones. And once again, we didn't actually need direct access to the sites we were flying. We just needed to get somewhere within visual distance once we got up in that man lift. So some of these we were flying up to a half-mile away from our launch and landing area to where we were actually surveying. We did have a 55-foot reach towable man lift. That way our pilot and observer could maintain visual contact with the drones due to the tall tree canopy. This is an FAA requirement. And then we used multiple ground control points that we established with a Trimble high accuracy GPS unit and correlated our drone sensors with in order to keep pretty good location capabilities. We used another cesium vapor magnetometer set up as a magnetic base station for correction of any background variations that would happen through the surveying time. For health and safety, we did daily inspections of the man lift, harnesses, lanyards, any critical components, and we followed all of our clients' requirements for working at heights. So now we'll move on to the pilot study results. This photo here is from our night operations. We were flying the thermal imagery that we'll get into a little later. First, we'll discuss the magnetometer results, and with that, I'll hand it over to Sam Kermis.
All right, thanks, Ron. So next, I'll go over some of the details and specifics of our aerial magnetometer survey. I worked on the project as geophysics support, visual observer, and data processor for the magnetometer data. So for the airborne magnetometer survey, like Ron mentioned, we set up a magnetic base station near the survey area and collected data prior to and throughout the survey area. If we were not able to find a spot outside the survey area, we were able to place that inside the survey area and mask it out of the data that was collected later on. But this magnetic base station was basically collecting background readings during the entire time of our flights so that they could be applied and as a diurnal magnetic correction to the data collected with the magnetometer later on. Our magnetometer hung approximately 9 feet below the landing legs of the drone. For flight altitudes across these sites, we flew, altitudes that ranged from 110 to 190 feet above the ground level. That's the magnetometer altitude, the drone being 9 feet above that. Line directions that we used for north-south and east-west. Line spacings varied 30 feet to 50 feet. We tried to collect the highest resolution data we could. So if there was a site that we had to fly higher due to visual, observation of the drone, then we would do a tighter line spacing. And as Ron mentioned, that man lift was 55 feet tall, but doing the reconnaissance with the drone ahead of time, we found that some of the trees in the area were 100 feet tall. So we didn't necessarily get above the tree line in many of the areas. So we could only go so far until we might have to set up in another spot where we can see the drone. And then tie line spacing. These lines were flown perpendicular to the main survey lines, and this is just to better tie the data together in data post-processing. Then photos on the left there, you can see the ground crew picture taken from up in the man lift. Jeffrey Hong there, our drone pilot for the project, and our drone and magnetometer. All right, here's an example of one of our survey areas. This was our largest survey area 1. This is 130 acres right here. So we split this up, like I said, into separate sections, north, south, and east, west, and this was due to visual line of sight, the trees being too tall, so that we would have to move to another location to finish the survey. Can go to the next slide. Here's an example of one of the flight plans or the flight path at Survey Area 1. This site we collected data over 2 days. This is day 1. You can see there on the left our takeoff and landing area, and the drone taking off to collect its line that we planned in the flight planning software. We collected on this day north-south lines, starting from west to east, until we couldn't see the drone any longer. We included a turnaround area of 150 feet to allow the magnetometer to straighten out before collecting the adjacent flight line. This drone was 200 feet in the air. If there's any wind, this magnetometer is only a few pounds, so any wind, can make it sway a bit. So when you make a 180-degree turn, you want to make sure that you allow it enough time to go straight so that it can, stop swaying before you start collecting the data that really matters. And then you can see there are tie lines. Day 2, you can see we started at that takeoff and landing area 1, and then when we couldn't see it anymore, we moved to an area inside of the survey unit and flew east-west lines. And there's the combined area 1 line path, 130-acre site. All right, next. All right, and when it comes to processing the magnetometer data, the data from the magnetometer and base station were imported into GeoSoft databases. A leveling script was used to remove any noise from the drone and swaying of the magnetometer in the air. The magnetometer and base station data was then cross-referenced so that we could apply a diurnal magnetic correction. Again, this diurnal magnetic correction was used to remove any daily variations in the local geomagnetic field. You can see in the photograph in the top right, that's the base station readings during an entire survey period. It didn't change very much, but we want to use this data to better zero out and create a baseline for our data so that some anomalies aren't higher than others when they shouldn't be. And then we removed known anomalies such as man lift, magnetic base station, vehicles, etc. And we picked the suspected well locations based on the center of the anomalies with the highest peaks. The table in the lower right, you can see the leveled magnetic readings during our flight and the areas there ranging from 130 acres to 10 acres, the altitudes flown, the total field low and highs, and then the range. You can see the range is higher in the higher acre. Closer to the surface or more area for variation. Here's an example of the data. These are some profiles of the data collected. You can see, we got the diurnal corrected data, the leveled data, the magnetic base station data, and for this profile, this is 33 minutes of magnetometer data, and then a snippet of where this data exists, and that I believe is survey area 1. We collected data from north to south, so you may think that it looks like a ton of anomalies, but really it's just it starts small, passes over the edge of the anomaly, goes back to background, and then each time you're getting closer to the center of the anomaly, and so on. So some of the results that came of the magnetometer survey, UAV mounted magnetometer was extremely useful for locating abandoned wells. The accuracy that we found was about 12.5 feet mean distance to the actual bore location when excavated with a 6.8 foot standard deviation, roughly the same as the onboard GPS 3-meter accuracy. It was proven reliable at locating casing depths at 180 feet below ground when flown at 150-foot elevation. Detection of these casings over 200 feet is likely possible. Improved detection of deep casings versus ground magnetometer surveys. Ground magnetometer surveys, of course, there's trees and all that. And if you don't have, if there's trees and tree cover, you don't have the best, GPS quality, which, when flying above the trees, you don't have to worry about that at all. We found that there was minimal difference between our 30-foot and 50-foot spacing. So, we could look to continue on with 50-foot spacing, depending on the needs of the project to speed up production. And the likely ceiling elevation for accuracy is about 200 feet for the drone. The table on the lower right, we were given coordinates for these suspected well bore locations from the state. They're shown there. And then the coordinates picked in the magnetometer data. We found that the actual versus state data ranged from 22 to 140 feet from the actual location versus the magnetometer data. These wells were found within 2 to 12 to 35 feet. So most of these that are around 12 feet are actually as good as it gets with a GPS of 3-meter accuracy. So right on. Here's some examples of the processed magnetometer data. Area 1 is 130 acre site there. is flown in approximately 7 hours total. You can clearly see where the anomalies are. And what's pretty impressive with this is the top of the casings are about 0 to 130 feet below the ground surface. And when flown at 190 feet, that means that we're able to detect these well casings, 320 feet from the magnetometer. In area 3 there, very similar. They stick out like sore thumbs. The center of the highest peaks were picked for those. And then with those state coordinates, a big enough buffer was used to make sure that we were able to map the entire area. And in Area 3's case, we just so happened to notice that there might be 2 more wells on that boundary on the eastern side. When it comes to magnetometer production rates, ground magnetometer versus drone magnetometer. For large sites like this, the drone magnetometer definitely makes sense, depending on what you're trying to locate. You got the acreage there of each of these areas. For a ground magnetometer in a wooded area, about half an acre per day is a pretty good estimate of how much could be mapped with one team. And to map a 130-acre site, that could take 260 days with one team, whereas our drone survey, we collected that area in 7.5 hours. So, you could get, what takes, a year on the ground done in just a few days with the magnetometer.
Thanks, Sam. Now we'll discuss the LiDAR results from our pilot study. This was a very efficient way to map ground characteristics and terrain. As you can see on the right-hand side is a picture of Areas 3 LiDAR point cloud before any filtering was done, which basically is all you'd see in a satellite photo where you can only see tops of trees. That is very dense, very hard to see through. The picture below that is once we remove the trees and change which response of the point cloud we're looking at, we then get to see our ground elevation data, which then reveals a creek and an associated floodplain area that is running right through the middle of the site between the two well sites, which if we are going to do remediation, we would have to do a permit based on this data to be able to build a temporary crossing and permit a temporary crossing to access the well site that's on the other side of the creek, because no other road in there exists. So the key takeaway of the LiDAR is it was very accurate. With that 0.2 foot accuracy, it was quite enough to show a lot of ground detail and really good for the surveying purposes we need at the site. And also, we were able to map that entire 20-acre parcel and every point of it in less time than it would take to do just a couple of simple linear cross sections through that creek or across an individual site. And we'll get to it on the next slide, where we had turned on hill shading, which quickly revealed any roads, berms, depression, ditches, and associated floodplains on the terrain. And we were also able to output digital terrain models and 1-foot contour elevation topo maps into our proprietary ParMaps GIS platform. And then crews are able to take our GIS maps real time in the field with the Esri Field Maps app and be able to navigate to these sites real time in the field, collect additional data, really just streamlines making sure the field crews get in the place they need to be to do their investigations. And so you can see here on the left is an example of a topo output of area number 2 with 1 foot contour lines. As you can see, there's some land elevation changes, but it really doesn't highlight any of the roads or any berms or any structures that you'd want to see. Now, the screenshot on the right-hand side of the data is with the hill shading turned on versus the topo contours. And as you can see now, you really get a good idea based on that black and white shading of what that ground is doing. You can clearly see all the forestry roads that divide that into transects and any other thing that's going on in that area. So it's a much better way of showing your elevations graphically than what a topo map would. And so then we process the data and put it into our ParMaps GIS system. And this is the combined LiDAR and magnetometer output. As you can see, we can have the heat map created by the magnetometer output and the hill shading and topo contours that field crews are able to go out with using the Field Maps app and navigate right to these. It really helps planning for remediation because you can see right where your wellbore is, right where you need to access, the direct route you need to access it. And you don't have to send somebody out there to do reconnaissance and traipse through the woods and try and find the best way to weave in and out of there and poke through that and really minimize the amount of trees you have to take down, the size of clearings you need to perform your remediation operations. It just makes it extremely efficient. And then you can take that one step further, like I said, for permitting purposes and even stormwater purposes for permits, where you can do a hydrological analysis based on that point cloud data, which is the image on the right-hand side here, where we ran the hydrological analysis on our digital elevation model from the LiDAR. And it shows that floodplain, all the micro drainage channels that contribute to that creek, and really just helps us once again plan the best access and footprint for our remediation efforts. Now we'll talk about the results from our pilot study where we flew the infrared thermal camera over the areas. We did data collection in the late evenings and late afternoons and evenings in order to reduce the thermal loading on the sites from the intensity of the sun and everything. This was done during the fall, so there was quite a swing between daytime and nighttime temperatures and when the sun was up and down. So we wanted to try and neutralize that or eliminate that as best as we could. We collected a very high image overlap, but however, the results were poor trying to map large areas because with that high image overlap and the slower speed of which we needed to fly the drone in order to get a fairly high resolution, there was a large delta temperature change between when the flight started and when the flight ended. So then we had to just take individual images that were captured over top of the well sites themselves and try and see what we could see from them. The thick tree canopy also very much buffered the temperatures, and we had thought that, you know, any buried concrete or indications of buried debris around these well sites may retain the heat and glow a little bit on the thermal flights from the solar loading during the day, or even maybe even seeing some escaping methane clouds with the differences in temperature. But ultimately, the thermal did not show that how we thought it may work. However, the thermal did show great differences between upland and wetland vegetation. The flights we did as example in the image below of the wetland and creek area You can really see where the edges of the wetland are, where that soil is saturated, and could be a good delineation tool. But overall, in this pilot study, the additional time and although this was the lowest cost sensor to fly, it was the most time intensive, and it just didn't justify the value of returns in trying to locate in our application here of locating abandoned oil wells. So in conclusion, aerial mounted LiDAR and drone remote sensing with magnetometers has a huge time savings and value for both state and federal projects, as well as private industry oil and gas projects. You can get the big picture results for multiple sites in the time it would take to conventionally survey only a single site. And this technology creates the real logical first step on, say you're a regulator and you want to find orphan wells for grant funding, or you have a problem area with some environmental concerns and want to see what's contributing to it. Well, you can fly the magnetometer and find if there's any undocumented orphan wells in that property. For private industry that has to go do some voluntary or even mandated cleanup of their former oil fields, this can really efficiently help you locate those wells based on whatever records, and we all know from mergers and acquisitions, old well records get lost and they may not even be available anymore. So sometimes it's just as hard to find these even in private industry as it is for on the orphan well side. And for both sides of the table, it allows very effective prioritization on very efficient site investigation, because you can locate these, pinpoint the location, send your crews right out, and really just hone in on that well right off the bat, instead of having to poke around or run gridded surveys all over a large clearing looking for where it may be. And then when you have all your data collected up front, your survey data, your magnetometer data, this is all data that can be used by all your subsequent phases of planning and remediation, and then even restoration, because you have all that those ground elevations shot and collected beforehand. It makes it real easy to go out and restore things back to the way it was, as if that oil well never happened. And like I mentioned earlier, the larger your queue of sites that you need to detect and investigate, that really drives down the cost and makes this very, very economical. Future things we're going to be working on are, we'd like to do some more flights in areas with higher target density and increased ground debris, really kick the tires on it and see what our limits are. We want to do more magnetometer surveys over wells with deeper casing, that 200-foot plus, see what is the limit of which we can detect the casing. We are working with airborne gas detectors and all the new changes on how methane emissions are going to be captured, carbon credits, and all of that. So we are getting into this, working on the space of performing carbon credits, facility surveys, and real total greenhouse gas emissions quantification. And then, as we all know how fast technology can move, we will, if any other sensor comes up that looks like it may help us, we will experiment with it. Another efficiency we could find is working with the FAA to get a beyond line of sight operations waiver. That would really increase efficiency and even safety by not then having to need that man lift. And then, of course, we want to digitize all future remediation sites and really bring them into the virtual GIS space, in that digital twin space, and really just move into that high resolution site characteristic that is starting to become standard with investigations. And with that, are there any questions? Thank you all for attending.
Thank you, Ron and Sam. That was a really great presentation on the challenges of finding these abandoned orphan wells, and also how we're, using technology to innovate and make it, easier to identify them and do it more accurately, more safely. If there's any questions, you can either raise your hand and we'll unmute you so you can ask your question live, or you can feel free to enter it in the chat and we'll read it out. So I see you got a couple people with their hands up. So Matt Owens, if you want to unmute yourself and ask your question, please go ahead.
Okay, I think I'm there. Thanks, Ron and Sam. I have a couple of questions. First one being, what is the turnaround time for FAA approval on these flight plans? And is one needed for each of these sort of surveys?
So we did not need to actually file FAA flight plans or anything like that. We were very, very far away from any airports or any, and we're, fairly low altitude where we weren't going to have an issue with any airplanes like that. But the stipulation is you need to have that visual observer to watch for any conflicting aircraft in the area, and then bring your drone back if you saw anything.
Gotcha. Okay. Second question is there an assumed minimum length of remaining casing in the ground for this to be successful? I mean, it's impressive that we can detect something that's the remaining casing is so deep, but is there sort of a needed length of remaining casing to get that kind of resolution?
We haven't found the limits of that yet. Even though, the wells that we're flying here are somewhere between 3,800 to 4,200 feet in depth and still had, several hundreds of feet of iron in the ground that we could detect because the different casing strings were ripped off and at all different depths. So there is, each one's unique and the magnetic field is going to put off based on what depths and however much casing's left in the ground. But ultimately, it all adds together into a detectable magnetic field.
Great. Thank you very much.
Thank you.
Jim Schutz, I see you have your hand raised. If you want to unmute yourself and ask your question.
Yeah, thanks. Really great presentation. I really enjoyed this. I find it fascinating that we can see pipe in the ground so deep. So I have two questions and one just sort of comment, which you don't have to address, but I'll make it anyways. So the first question, and maybe this was covered, but what is the difference in depths of detectable abandoned wells between a ground survey and the drone survey? So that's question one. Question two, in the one flight path and area that you covered that had sort of an L shape to it, you moved your man lift into the flight path, and I didn't see any indication of a magnetic field from the actual man lift. So when I saw they had to move the man lift, I thought, oh, I wonder if there was some background noise or something. So if you could comment on that. And then lastly, the thermal detection of surface water, I think is awesome, because being a hydrogeologist, one of our groundwater discharge techniques is looking for groundwater discharge with thermal. So you actually were able to show it not necessarily on a seasonal scale, but almost on a diurnal scale, where the temperature change during the day was able to detect that. So thank you very much.
Thanks, James. So the first question, typically, at least what we deal with here, is on most of these oil well sites, it's the limited clearing size, and a lot of times these things are right next to a large drop off or a hill or 20 feet away from a river, things that really limit how and where we can lay out a survey grid on top. So basically, if you had a well in a nice open field, yes, you could do a 300 by 300 or a 400 by 400 survey grid and walk all those ley lines and see the deeper casings. But what we typically deal with in the real world in these old oil fields is, we struggle to sometimes get an 80 by 80 survey grid over these sites before we're into the thick brush or walking into a river or things like that. So really that's a limiting factor with the ground surveys is where you can walk. Because the deeper the casing, the larger of a survey grid you need to either walk or fly over top of it to see the entire anomaly. And as like you saw in the presentation, some of those anomalies can be 400 plus feet in diameter, that we need to pinpoint the center of. And if you can't see the whole picture, all you're seeing is a little snippet of the center of that anomaly, and you're not seeing much change in slope to that magnetic field, so you really can't pick out where the center of it would indicate the center is the wellbore. And then for your second question, because of the tree height, we had to move into the survey area because that was that's because of the tree height. We were starting, as we were moving from west to east with our flight lines, we started getting to the limits of what we could visually see the drone flying at 190-foot elevation, which we wanted to stay below. So we had to move our man lift operation over in order to then continue that survey further to the east and be able to see the drone. So we did have to set it on, the only available clearing in that area was the former tank battery site. And so from that, because that's a known magnetic anomalies, basically Sam filtered those out and leveled those anomalies from our vehicles and the man lift out of the survey.
Yeah, for that, in the initial data, it was seen in the data, but since we know that that's a known anomaly, we were able to mask that out.
Okay, for our next question, Carrie Ross, I see you have your hand up. If you want to unmute yourself and ask your question, please go ahead.
Hello, yeah, thanks. Great presentation. I was just wondering in regards to the thermal data collection, if there's any anticipation for enhancement in that process. It seems like there was some poor results, and just wondered, that application would be really helpful for a lot of the munitions cleanup sites. And yeah, I wonder if there's any work in progress to improve the thermal data collection.
None I know of at this time. If it was a lot less of a treed canopy environment, our results may have been different. But this is pretty representative to what we run into. So, it's probably moving forward not going to be one of our first choices of tools to pull out of the toolbox. Because that magnetometer worked so well. That is really more of the silver bullet kind of defining these old things.
I see we have a few questions that are in the chat. The first one is from Michael DiSavato. In assessing areas for utilizing this technology, are there any characteristics that are known to likely offer more anomalies or perhaps require different techniques or additional overlays?
Yeah, so where we're working at here in the area of this pilot study, this state did have pretty good regulations. They had permitted wells to be drilled on basically uniform spacing patterns. Now, if you get into other areas, say the Appalachians, where and some of the real early boom states before regulations caught up to the oil drilling industry, where you may have multiple completions or multiple wells on the same well pad, then you'll have to get a little more scientific and change your methods a little bit if you want to pinpoint those wells out, because their magnetic fields will essentially be overlapping or combining into one. Then yes, you would have to change some of your tactics, little bits, kind of planning, knowing a little bit about what you're getting into, and what the well density and anomaly density is going to be going in there, which there generally are enough records where you can get a good idea of that. But definitely in, your Texas, your Appalachian states, some of your early boom states, Pennsylvania, West Virginia, If you do a flight, you're probably going to find a lot of wells you didn't know were there.
Okay, next question from Glenn Ulrich is, what is the likelihood for the casing of wells to have been removed to depths greater than 200 feet?
Very likely. We have run into those quite a bit. To do the remediation and the plug and abandonment, a lot of times with these early era wells, because they pulled all that casing out, we have to almost reconstruct and re-drill a well and recase it in order to properly abandon it and then cement it back up. But yes, we've done many where there's no casing at all in the hole for 1,500 feet because originally when it was drilled, it was not cemented in, and it was able to be easily pulled right out when they plugged the well. So yes, very, very common.
And the last question we have is from Jeff Dietrich. Is there a distance limitation from the launch or landing point that we can fly the drone to survey an area?
At that point, it just becomes the range of your battery. Generally, we were getting about 35 minutes from a battery flight, battery life out of each flight, and it took us about 10 minutes to land, to bring the drone back, land, swap the batteries out, and get back in the air. So I mean, there is a distance limitation there, but generally, it's for the most part what still keeps you in and you and your visual observer within the range of your sights. I mean, like I say, we were some of these we were moving, quarter, half mile away from where we were set up before our surveys even started. So it does allow you to think outside the box quite a bit.
So that's all the questions we have at this point. If anyone else has a question, please feel free to reach out to Ron or Sam directly. Their email addresses are listed on this slide. A link to the PH form has been posted a couple times in the chat. If you have any issues downloading that, please contact us. And if you miss any questions, there'll be the recording of this webinar posted on our YouTube channel in the next few days. If you can go to the next slide, please. So our next webinar will be on October the 11th at the same time as today's, presented by Heather Budzik on Inactive Landfill Initiative, Impact of PFAS and 1,4-dioxane on Drinking Water Sources. So we hope you can join us for that. Thank you to everybody who joined us today, and we hope to see you again in October.